Hello, everyone. Welcome to the ILTA Physics online lecture problem solving session. Today, we're going to study free fall. Free fall is a special kind of one-dimensional accelerated motion where a constant gravitational acceleration pulls an object vertically downward. Think about bungee jumping from a high bridge, just like in the picture on the right. It's just common sense. You jump off a bridge and you fall. We don't even have to think about it. From a kinematic perspective, however, this happens because gravity pulls the object downward, toward the center of the Earth. We can explain that this constant pull creates an acceleration, and the falling motion can be analyzed as an accelerated motion. The free fall problems we'll solve today are actually quite simple if you approach them as one-dimensional accelerated motion in the vertical direction. We'll look at two types: true free fall, where an object falls from rest from a high place, and vertical projection, where an object is thrown upward and slows down due to gravity. Now let's briefly summarize the physical concepts and formulas related to free fall motion. Free fall is a one-dimensional motion with constant acceleration. It's special for two reasons. First, the movement is vertical, and second, the acceleration is always gravity, which has a constant magnitude and a constant direction. I've explained the detailed concepts of physics and derivations in my theory lecture, so here, we'll just focus on the formulas and problem-solving strategies. Since free fall is a form of one-dimensional acceleration, all the kinematic formulas we derived earlier still apply. Just remember that the acceleration is a constant, g, directed toward the center of the Earth, which is downward. To accurately use these formulas, we first need to set up a coordinate system. As a quick review, remember that setting up a coordinate system includes choosing the origin and deciding which direction is positive. Depending on the problem, you can choose any coordinate system that makes the math easier. However, for free fall, using a standard Cartesian coordinate system is usually the most effective. This means we naturally define the positive direction as to the right horizontally and upward vertically. Since we are focusing only on vertical motion today, we will set the upward direction as positive. This also implies that the direction of gravitational acceleration is negative. When we plug it into our equations, we must use the value minus g. Please keep in mind that in our calculations, gravity will always be negative 9.8 based on this coordinate system. Now let's look at the three main kinematic equations for one-dimensional accelerated motion that we already know. First is the velocity equation. The final velocity of a falling object is the sum of the initial velocity and the product of acceleration and time. In our system, gravity is opposite to the positive direction, so it's written as minus g and calculated as negative 9.8. Next is the position equation. Since the movement is vertical, we usually use the variable y. The final position is the initial position plus initial velocity times time, plus half of the acceleration times time squared. If we want to calculate the displacement caused only by gravity, ignoring initial position and initial velocity, it looks like the equation on the right. Again, be careful to represent gravity as minus g. Finally, we have the equation relating velocity and displacement without the time variable. Since displacement along the y-axis is often thought of as height, we sometimes use the variable h. These three equations aren't new formulas. They are exactly the same kinematic equations we've used before. Just be mindful that acceleration appears as minus g because it points downward. Now, let me explain some important strategies for solving these problems. Another crucial decision for actual calculation is where to put the origin of your coordinate system. You can pick any position as the origin to make the math easier. However, in my solutions, I will always set the object's initial position as the origin to keep things consistent. The top right image shows the most basic type of free fall. an object is dropped from rest at a certain height. In my method, the yellow dot, the starting point is the origin. In this case, the final position, y, will be a negative value because the object ends up below the starting point. The two images below show other types of motion. In these cases, an object is thrown upward, reaches a certain height, and then falls back down. Even here, if we consistently set the starting position of an object as the origin, the y-coordinate will be positive when the object is above the starting point and negative when it's below it. If an object is thrown straight up from the ground, as shown on the right, and we set the starting position of an object as the origin, then the y position will be positive at all times. I'll explain this more during the actual problem solving. Here are 3 important tips for your calculations. First, if an object is dropped from rest, the initial velocity is always 0. This is a hidden condition you should always look for. Second, if an object is thrown upward, its velocity is exactly 0 when it reaches its highest point. If you think about it, the object goes up, stops for a split second at the peak to change direction, and then falls. That's why the velocity is 0 at the very top. Third, when an object moves up and then back down, the speed at any given height is the same on the way up as it is on the way down. Only the direction is different. For example, if you throw a ball up with an initial velocity v, I, when it falls back down and passes that same starting position, its velocity will be minus v, I. If you use these properties well, you can solve most problems easily. Now let's solve some basic free fall problems together. Problem 47 is about the motion of a gannet. A gannet flying over the sea spots prey and dives vertically into the water. Its speed when it hits the water surface is 32 meters per second. We need to find the height from which it started. The first step is setting the coordinate system and the origin. Since it's linear motion, we'll use a Cartesian system where up is positive, and we'll set the initial position, the yellow dot, as the origin. Let's do the math. Since we don't have a value for time, we'll use the velocity displacement formula. The hidden condition here is that the bird starts from rest, so the initial velocity is 0. The final velocity is 32 meters per second. One thing to keep in mind here is this. Since the bird is moving downward, the negative direction in our system, the velocity is negative 32. Gravity is also downward, so we plug in negative 9.8. Solving for h, we get minus 52.24. This negative value represents the y-coordinate relative to our origin. Therefore, the height the bird fell from is 52.24 meters. It's a really simple problem, but please practice setting the origin and correctly applying the signs for velocity and gravity. Problem 48 describes a trout jumping vertically out of the water. If the trout leaves the water at 8 meters per second, we need to find how high it can jump and how long it stays in the air to reach a waterfall that is 1.8 meters high. Even though the fish is moving upward, gravity is pulling it down the whole time, so we still treat this motion as a free fall type problem. Before we start the calculations, let's set up our coordinate system. We'll use the standard Cartesian coordinate system again, and we'll place the origin at the trout's initial position. First, let's find the maximum height. When you hear maximum height, you should immediately think the velocity at the top is 0. Again, since we don't have time information yet, let's use the velocity displacement formula. The final velocity at the peak is 0, and the initial velocity is 8 meters per second. Notice that the initial velocity is positive because the fish is moving up. Calculating this gives us an h of 3.27, so the height is 3.27 meters. Next, let's find the time it takes to reach 1.8 meters. We'll use the position equation. The initial position is 0 because that's our origin. The initial velocity is positive 8. Plugging in negative 9.8 for gravity, we get a quadratic equation for t. Solving this quadratic gives us two values for t, 0.27 seconds and 1.36 seconds. So, what exactly do these two values mean in terms of physics? Since the trout moves vertically, it passes the 1.8 meter mark twice. Once at 0.27 seconds on the way up, and again at 1.36 seconds on the way down. So, the time it could be at or above that waterfall height is up to 1.36 seconds. Make sure to practice different types of problems by setting up your coordinate systems and origins carefully. That's it for today's lecture. Great job, everyone. I'll see you next time.